Okay, thank you very much for the invitation. This is a joint work with Umberto Irinievich. And the idea here is to study Hebb flows on RP3, which are dynamically convex. And the main motivation for this study is probably the restricted three-body problem. And so I will show an application on that systems, in particular to the lunar problem. And also, in fact, the first application is related to the existence of these open book decompositions, which organize the flow in a nice way. So that this open book lies really on RP3. You don't have to lift to S3 and find an open book there and conclude some of the properties of the dynamics. You look this open book directly on RP3. This is the idea, the main motivation. And also, this result gives some information about multiplicity of Hebb orbits and something related to ellipticity of. So this is another motivation. And also about the existence of Hopf links. And finally, if I have some time, I will say a little bit about such dynamically convex Hebb flows on more general length space. So I repeat all these definitions that M is a closed connected three manifold equipped with a contact form lambda. And we consider the Hebb flow of lambda. And C will be the contact structure associated to this contact form. Okay, so this is the definition of the Rev vector field, and we consider its Hebb flow. Okay, the example will be the simplest one, which is a star-shaped energy level on R4. If we consider this one form in coordinates Q and P in R4, then its restriction to a star shape with respect to the origin. I mean, the restriction, I mean the pullback by the inclusion map. Then it's a contact form on this star shape S. In particular, it's a contact form on S3. Okay? And C0 will be the associated contact structure. This is the contact manifold that we are considering. Just to remind that we could fix the manifold and the contact structure and multiply our contact form by a smooth positive function and study the Hebb flow associated to this other contact form, which is equivalent to study the Hebb flow on a star-shaped hypersurface just by dilating the points on S3 by square root of this function f. Okay? So we fix S3 and consider this family of contact forms there. Okay? So, but to talk about S3, let me just define it. I will define it. RP3 as the quotient by the antipodal symmetry, identifying the point Z with minus Z on S3. So this is what I call RP3. And because of this form of the contact form, we see that the contact form lambda naught descends to a contact form on this quotient here. And so we also have a contact structure on RP3. Now this is exactly the contact structure, which is called universally tight, that we will consider in this work. So just to remind that RP3 is equal to SO3, which is this very particular example of length space L2 and also coincides with the unit tangent bundle of anything lemmetric on the two sphere. Okay. So again, we could just multiply our contact form on RP3 by a smooth positive function. Consider its Hebb flow. It's equivalent, not exactly equivalent, but it corresponds to considering symmetric star-shaped hypersurface on R4. Okay, let me just try to draw the picture of the object that we are looking for. So S3, we see it inside C2 with complex coordinates Z1 and Z2. And we can consider these two knots inside, S1 cross 0 and 0 cross S1, L2. These are fibers of the Hopf vibration. And if we consider the Hebb flow associated to lambda naught, they are also periodic orbits of that flow. Okay, as we will see, they are unknown, and there is this other number that Richard has defined. I will not define it. The self-linking number of such knots are -1. I will just call them Hopf fibers, okay? And here is the picture, which it's defined such maps, disk maps, into S3. For each C, an element of S1, you can define this map here, and this is the picture of the projection of such maps in both factors of C2. So here we see just a segment, and the second factor is just the identity map, and projects like that. And this disk on S3, the boundary is mapped into the Hopf fiber L2, this one. So you see here in the picture, the blue guy here is this Hopf fiber. It's just 0 cross S1. So C is an element of S1, and we could vary here along the circle. We would obtain distinct disks foliating all the complement of L2 inside S3. And all such disks are embedded. And all such disks are transverse to the Rib vector field associated to lambda naught. So this is an example of what I call an open book decomposition with disk-like pages. And moreover, each one of those disks are global surface of section for the Hebb flow of the standard contact form on S3. Now, just to define something which is analogous on RP3, we can consider the quotient of this family of disks to RP3 and see what's happening. So it's not difficult to see that when we identify the antipodal points here, this knot L2 here descends to a knot on RP3, but it's a 2-to-1 map. So double cover this knot on RP3. But when we see the projection of those disks to RP3, it's slightly different, because here you see that these disks correspond to segment. There is nothing this other side of it. And so these disks descend as embedded disks, at least in the interior. So on RP3, we could also consider this family of disks, which is again an S1 family of embedded disks. And all of those disks approach the boundary, that not the projection of L2, as a double covering. So the picture on S3 seems like that. It's just L2, which is the binding of this open book decomposition with disk-like pages. And the flow determines a first return map for each of the page. But when we consider RP3, it's almost the same thing. The difference is that the disk is, again, this family of embedded disks. They are approaching this knot as a double cover. Okay? So this is so this knot that we see here is what we call a 2-a knot, because that emits this two disk, which is embedded interior and double cover in the boundary. Okay. Okay, we could have projected also L1. It would be the same thing. It would be also a 2 and not with a similar one-parameter family of such disks, providing another open book decomposition of RP3 with disk-like pages. So this is just adapted to the standard contact form on RP3. And the self-linking number, there is a definition. In fact, it's slightly different definition. It's called rational self-linking number, which is, in this case, it's just -1/2 instead of -1 as in S3. Okay, now any such 2 and not, I will just call, for simplicity, a hop fiber. And we are looking for global surface of section, which is, there is this rational word, which means that, so a disk-like global surface of section for a Hebb flow on RP3, lambda here is just one smooth positive function times the standard contact form there. So a disk-like global surface of section, just one of such disks, so that the boundary is a periodic orbit for the Hebb flow, and the interior of these two disks is transverse, the Hebb vector field, and you have a first return map. All trajectories outside the boundary will hit this disk infinitely many times. So since this disk preserves an area form, it has a fixed point, and also in this situation you have another, let's say, hop fiber, which is transversely isotopic to one of those special hop fibers that I showed before. Okay, now with that picture in mind, we are very close to the result that we get. So a contact form on S3, as usual, is you just look at the Conley-Zender index of all periodic orbits. If they are at least 3, then you say that it's dynamically convex. And the same thing holds on RP3, but you have this condition that you look only at the contractible periodic orbits, and you assume that the index is at least 3 for all the contractible, then you say that the contact form is dynamically convex. So there is some nice thing with RP3 is that it emits a global trivialization of the contact structure, and still can measure the Conley-Zender index with respect to this trivialization, and some of the orbits might have, which are contractible, simple and contractible, they might have index less than 3, but when you take the double cover, which makes them contractible, then the index is at least 3. So this is the definition of dynamically convex contact form on RP3, which is basically, you just lift the flow to S3 and you use the definition for S3, for the Hebb orbits upstairs. So the nice theorem, which many people mentioned before, Hofer, Vysotsky, and Zenders, if the hypersurface is strictly convex on R4, then the flow, the contact form is strictly convex, is dynamically convex. Okay, let me just remind this theorem, this big theorem by Hofer, Vysotsky, Zender, which is more or less the theorem that we're going to obtain for RP3, which says that if the contact form is dynamically convex, then it admits a closed orbit, which is unknotted, self-linking -1, and has Conley-Zender index 3, which is the binding of such an open book decomposition as I put it here. And then also each page of this open book is a global surface of section. You have all this two-dimensional reduction that allows you to conclude that there are 2 or infinitely many periodic orbits in the Hebb dynamics. So again, this picture here, each page And the theorem that we have is the other picture that I showed you when you project that foliation to RP3. It's basically the same theorem with some extra information that it's a bit a small advantage, which is the following. So assume that the contact form on RP3, which is L21, is dynamically convex. So then it admits these two unknotted periodic orbit, so that when you iterate it twice, its Collinsender index is equal to 3, and it's the binding of that rational open book decomposition with disk-like pages. Each page is a global surface of section for the flow. Okay, so there is this extra word here, which we gain, which is that the binding orbit of this open book decomposition is elliptic, which in the case of S3 you do not know. And the reason for that is that when you iterate twice, elliptic here means elliptic or parabolic, means non-hyperbolic, might be parabolic, as in the S3 case. So the reason is just that if you take a hyperbolic periodic orbit and iterate twice, then the index should be even, but the index is 3. Okay. Okay. This is the first part of the theorem, the existence of that special binding orbit for the rational open book decomposition. The second part is sometimes you have in your hand a periodic orbit, and you might want to know if that's a possible binding orbit for the open book. And this is what it says here. If you take one of those hop fibers, which is a two unknotted periodic orbit, self-linked minus 1/2, then, assuming that the form is dynamically convex, then you find this rational open book decomposition with prescribed orbit. That's in particular, for instance, the fixed point of the first return map is one of such orbits. It also admits the open book. Okay. This, I will give an idea of the proof. In fact, maybe later. First, I would like to say something about the applications of this theorem. Okay. So again, this is a condition for the existence of this finite energy foliation on the symplectization of RP3. This could be a first step to understand more general finite energy foliations on RP3. So the simple, not strong, but not so strong condition of dynamical convexity. And so let me just remind, Urs and Otto explained to us a lot about the three-body problem. I just reminded that we have three masses with these symmetric forces acting on them, and with this inverse of the distance square, and the equations of motions of these three bodies. Imagine that they are all in the same plane. The motion is on the plane, and the Newton's law will give that the second derivative of the position is the sum of the forces at each mass, and this divided by the mass. And this gives this system of differential equations. And we try to understand this. Even in the plane, it's extremely hard to understand it. But we see the third equation here. It's the third mass. That there is this M3 multiplying all the terms here. We could just cancel it. Okay? And take the limit when this M3, this third mass, goes to 0. And we would still have a differential equation describing the dynamics of the third body and also of the others, the first two bodies here, M2, M1, and M2, which is a Hamiltonian system of the form kinetic plus potential energy, with P equal to the momentum, M times the velocity. Okay, so taking M3 going to 0 and considering this equation in the limit, we would find a very simpler equation of motions. And here we don't see M3 anymore, but here we see that the first two bodies, they behave as in the two-body problem. So we could just, the third body does not influence anymore the first two, and we could just solve this equation. It's not so difficult there. The conics and so we, in this restricted three-body problem, we prescribe the motion of the first two bodies, and then the problem is to understand the motion of the third body. All in the plane, M3 is equal to 0, and we assume, moreover, that the first two bodies, the primaries, they move along circular trajectories around their center of mass, like here. So this is not a bad assumption for our system Sun-Earth, because they move almost in a circular trajectory. And the third body with no mass would be the moon. Okay, so the problem is to understand the motion of the moon. And the lunar problem would be to understand the motion of the moon close to the Earth. Okay, so, but here, so since we prescribe the motion of the Sun and the Earth as circular trajectories, the equation of motion of the third body depends on time. So to avoid this problem, we just fix a rotating system which rotates together with the first two bodies, with the primaries. And with respect to this rotating system, the two primaries stay at rest, okay? They are aligned with the center of mass. And then we describe the motion of the third body with respect to this rotating system. Now it does not depend on time anymore. It's a Hamiltonian function. We describe this motion, and we gain here this magnetic term corresponding to the Coriolis force. And these other potential terms here are related to the two primaries. Okay? So with respect to this rotating system, the Earth, I changed here and put a parameter, which is the mass. The mass of the Sun is mu, and the mass of the Earth is 1 minus mu. Okay? And mu is close to 1. It's in between 0 and 1. This parameter we consider close to 1. Okay. So, so the motion of the third body depends on, of course, the energy and the parameter. Let's consider that the moon has low energy. And if the third body has low energy, then, so here is this black dot here means the Earth at rest, which is at the origin of the system. I'm just plotting the Hills region on the plane for low energies. So either it stays trapped close to the Earth, either the third body stays trapped close to the Sun, or stays far away in an unbounded region. So I will consider just this region where it's close to the Earth. So this is the lunar problem, okay? To look at the flow here. So there is, so here, Otto showed some numerical simulations, and we could see that, well, maybe there are collision orbits of the third body with the Earth, collides the origin here. So there is this Levi-Civita regularization which regularizes these collision orbits. Okay? And so to do this regularization, instead of using these coordinates Q and P, we change it for U and V. Okay? And there is this nice formula, which is a symplectic change of coordinates. And we can consider the Hamiltonian written in this, there is a term multiplying just to slow down the orbits which are colliding. And we obtain a different Hamiltonian function which describes now the motion of the third body in this regularized system. And in fact, we put C here, which is the energy, as a new parameter. So this Hamiltonian makes sense when we consider this function here to be equal to 0, at the 0 energy level. So we see that when we regularize the system, there is this square here, which makes that the region that we see here, which is non-compact due to the collision orbits, now it's regularized as a sphere-like hypersurface in R4. So after all these changes in the three-body problem, with all those assumptions, we are back to Hamiltonian flows on sphere-like hypersurfaces in R4. And because of that, this expression, we can see that if you take u and v, or if you take minus u and minus v, it corresponds to the same point of the original system. Okay? So this level is symmetric. So the flow in this sphere-like energy level corresponds to a flow on RP3, because this energy level is symmetric with respect to the origin. Okay? So I would say that if you want to study the three-body problem with all such assumptions in the correct way, you should understand the flow in RP3. Of course, you can use the lift to S3 to look at the flow here, but I think the correct way to study it is to look at RP3, the flow on RP3. Okay, so how can we apply our theorem about the existence of those rational open book decompositions to this situation here? The only possibility is if you can compute that such sphere-like hypersurfaces are dynamically convex. And this is done by these people, Peter Albers, Joel Fish, Urs Frauenfelder, Helmut Hofer, and Otto van Kort. They proved that for low energy, in fact, if you fix all energies, you fix an energy below, this is a critical value of the rotating Kepler problem, so we fix an energy below here. Then for the mass of the sun almost equal to sun, almost equal to 1 means the mass of the Earth almost equal to 0. So for an interval with fixed energy here, this sphere-like hypersurface is strictly convex in geometric sense. So in particular, it's dynamically convex. We can apply our result to the quotient manifold, to RP3. Okay? And then this would be the first application of that theorem, which says that, so we have this special elliptic orbit, which is the boundary of this rational open book decomposition for the planar restricted circular three-body problem. And this binding orbit is elliptic. And each page is a global surface of section. And moreover, an application of the second item of the theorem, if you give an orbit there, and if you know that it's a Hopf fiber on RP3, then you would also obtain, for the convexity range, that region that I showed you that's dynamically convex, you would know that any given Hopf fiber inside there is also the boundary of all the same thing. In particular, if any fixed point of the first return map satisfies that condition. So this is direct application of your theorem. Okay, then I will just, I try to draw your picture here to remind that Urs have just raised a question here during his talk about the retrograde orbit of Birkhoff. it is the boundary of a disk-like global surface of section. This, at least for the convexity range, if this picture that I put here is correct, then this is a Hopf fiber inside this RP3, not on S3, inside the RP3, and this would be with the within that range of energy and parameter would be, so it would be this, would be true. I don't know if it was known or not, but maybe close to the Earth. I don't know if it was already known, the existence of this global surface of section for the retrograde, the Birkhoff. Sorry? Okay. Close to the Earth. Okay. Okay. Yeah, so here is close to the Sun or to the Earth. Okay. So close to the Earth, which is the one that we obtain here. So if it's new, then it's a very, it's an answer to a very fraction of Ur's question. Okay, so that's the application that we have here about the three-body problem. Maybe we gain another application. And let me say something about geodesic flows on the two-sphere of a Finsler metric. So the application of this theorem there is the following. Suppose you have a Finsler metric on the two-sphere, and let R be the reversibility of some measure of how much the fibers are non-symmetric. It's at least one. So if the flag curvature of the Finsler matrix is pinched in this way here, then the head flow on the unitangent bundle, which is RP3, is dynamically convex. Then we have the application of our theorem, which says that we have these two annotated elliptic closed geodesic. And moreover, well, with all the structure of the flow of the open book decomposition, and moreover, it's possible to say that this is simple. Right? Let me just remind that this theorem was proved by Rademacher. I mean, the existence of the simple closed geodesic under that pinching condition is proved by Rademacher, an elliptic orbit also. Of course, the part of the proof that it's new here is this existence of the open book decomposition, and of course, the second orbit that he obtains, because with this pinching condition, Rademacher also obtains a second closed geodesic. It's in our case, you can say that it forms a Hopf link. There is this elliptic and the other one forming a Hopf link. This would be an extra information about this Rademacher's result. Okay. I must mention that this pinching condition implies dynamically convexity because it was computed by Harris and Paternai, that this is true. It is an application of our theorem and also an application of this Harris-Paternai theorem. It's very important to use this information here. So this includes, for instance, for Riemannian matrix, the 1/4 pinch, where R equal to 1. Okay, almost there. Okay, maybe I should just comment a little bit about the proof. Is the following. Let me go back to that here. So the proof, of course, we make use of holomorph curves in the symplectization. Okay. Adapted to the almost complex structure is adapted to the contact form. And so the way we prove is the following. You just have to find a finite energy plane just one, which is embedded, and it's asymptotic to an index 3 orbit. You just have to find this plane. Why? Because there is this assumption that it's dynamically convex. So let's look at this asymptotic. What could be this asymptotic orbit of the finite energy plane? Could be, okay, simple, just a simple orbit. It could be the double cover of a simple orbit, or it could be a higher cover. Higher cover, it's not possible because of the hypothesis of dynamical convexity. If it's a higher cover, then the Conley-Zender index should be high, at least 5. So there is just two possibilities if you have this plane. Either the asymptotic orbit is simple, or it's a double cover of a simple one, which is non-contractible. Only these two possibilities. But if the asymptotic orbit is simple, then it's possible to show that that periodic orbit is unknotted because the plane is embedded. And it's self-linking -1 because it forces that the projection is transverse to the Hebb vector field. And if you use the characterization of the type 3 sphere that Richard has mentioned in his talk, then you would conclude that the manifold must be S3, okay, with the existence of that plane. Should be S3 if the asymptotic limit is simple. So it cannot be. Must be the double cover of a simple periodic orbit. And this periodic orbit must be non-contractible, otherwise the index should be at least 5. So all we have to do is to prove the existence of this very special plane. It's a finite energy plane, asymptotic to an orbit with index 3, and it's embedded. It's very important to be embedded. And the way we do this is the following. We consider a cobordism, interpolating our contact form here, and a contact form associated to an ellipsoid in a monotonic way. And for the ellipsoid, we construct that special plane. And because it's asymptotic to an orbit with index 3, the double cover of a non-contractible one, then it lies in a two-dimensional modular space that we push it down to solve our equation. So when we do that, we have to use all the machinery, like SFT compactness theorem, Symfries intersection theory, asymptotics, algebraic invariants associated to these curves. The first point is that this two-dimensional family cannot break in the middle because there is no space here. The action does not allow a breaking in the halfway down. So we can make an element of this family, have the lowest R value to go to -infinity, and then look at the building it produces. Here is the cobordism again. And here is just a symplectization of our contact form. The building must be very simple. It should be, here we have this orbit of the ellipsoid, and we would have just a cylinder here and a plane. Downstairs. And this is the plane that we are looking at. We use all those algebraic invariants to show that this is embedded. And this must be asymptotic to an index 3 orbit. Okay? There is no space to be. The problem would be if this asymptotic limit had higher Conley-Zender index. Then we could not control anything. Our theorem was over. Okay, this is the main idea of the construction. Then I was going to mention a result for length space. Oh, okay. So it's just a generalization of the RP3. We consider a ZP action on S3, which rotates each complex factor by 1 over P and Q over P, where Q is at most P and relatively prime pair of integers. And then we take the quotient of S3 with respect to this action. Again, the standard contact form on S3 descends to a contact form on LPQ. And the problem here is, at least so far, we had some difficulties to prove this theorem for general length space, which means that we were not able to find this very special periodic orbit would be a P-n knot, so the analogs of the Hopf fiber for LPQ, which would be this P-n knotted orbit. This part of the theorem, unfortunately, we could not produce due to some difficulties. And but still, if you find a periodic orbit, if you have it in your hand, one of these P-n knotted periodic orbits, self-linking number minus 1 over P, if you have it, and if the flow is dynamically convex, meaning that if you lift to S3, it is dynamically convex, then for that given periodic orbit, you have this spanning open book decomposition. All pages are global surface of section. You can have a very similar picture as in RP3. This, in fact, was a theorem proved before with some extra assumptions with the Umberto and João Alicata. And we just, one part of this theorem is to pass to the degenerate case, which requires a lot of analysis. Okay, so this is what we can do for general length space. And I think my talk is over. Thank you.